Assalamualaikum and a very good day to everyone and doctor. So my name is Alana Syahada binti Muhammad Zamri and I am from group 4. Today I will be presenting the solution and analysis result for the assignment 1 task 3, which is the focus of this presentation is a comparative analysis between two specific tree data structures, which is binary search tree (BST) and S-play tree. Before we dive into the code and results, here is the agenda for my presentation today. So first, we will establish the theoretical foundation by looking at the key differences between BST and SPLAY. And then I will introduce the project background and then the specific project functions of the system I have built for the demo. And then we will move into the coding and system demo, where I'll show you the output of the program. And finally, we will discuss the core of this task, which is the experiment on scalability and performance comparison for BST and SPLAY, followed by a detailed output analysis and my conclusions. To understand our results, we must first understand the fundamental differences between these two structures. So we have BST and SP3. So first, let's look at the structure. So in BST, it is a binary tree sorted by key, while SP3 is self-adjusting BST. So this is a critical distinction. Regarding balancing, in BST, balancing is not guaranteed. If we inserted sorted data like 1, 2, 3, 4, 5, a BST can degrade into a linked list, leading to performance. In contrast, a S-play tree more frequently access nodes to the root, so it doesn't strictly balance high in the AVL sense, but it optimizes for access. So as we can see here, worst case high, BST is O and aspect is also O and is worst case snapshot, but this rarely happens in practice due to S-playing. While search, insert and then delete time, a BST takes OH dependent on height. If the tree is skewed, this is slow. While the SP tree, however, has an amortized O log n complexity. This means that over a sequence of operations, the average cost is logarithmic, even if one specific operation is expensive. And then best use case is we use BST for random data with uniform access, but SP tree are superior when have locality of reference, meaning we have repeated access to specific keys and the SP tree brings them to the top for instant retrieval. Moving on to the project background, the objective of this task was to demonstrate how the use of tree-based data structures manage real-world data, specifically in this team that provided by Doctor to our group is student and cost management. We wanted to verify how different structures affect three specific metrics as stated in the slide here: data retrieval speed, insertion performance, and scalability when the data grows. So the system implement the binary search tree as the main application. So in the task 2 that we have done and introduced the SP tree here specifically for comparison purposes in this task. So next here is the functional overview of the system. So the user interacts with a system switching module, allowing them to toggle between the BST mode, SP mode, or the benchmark module. So let me clarify here, as stated in the report, and then as requested, this is for a prototype version only, which is for the system demo. So under the student management, we can add, search, delete students using either BST or SP logic. Similarly, we have cost management to handle the cost records too. So similar, what we call functions. So however, the highlight for task 3 here is the benchmark module. This module is just for the comparison analysis where automatically inserts and records. We have 4 and records. Later we will go further. And search and records to compare the performance of BST versus S-play, displaying the time result directly to the user. Okay, now let's look at the experiment design. So the purpose was to measure how both trees perform when the data size grows. So we tested 4 distinct data sets, sizes n, which is 500, 1000, 5000, and 10,000 records. So we measured the insert time and the search time metric in the microsecond. So our hypothesis was that the SP tree would keep the effective access path shorter, resulting in faster operation to areas. The BST might become skewed and drop in performance. So next, this is the coding and demonstration. So I'll be really fast here just to show the coding and the system output. So we can see here, we have added, which is for the benchmark module, for us to see the comparison between BST and S-play tree. So we have the test sizes here, 500, 1000, 5000, and 10,000. So this is to compare between BTS insert and BST inserts, SP insert, BST search, and SP search. So then we'll display the result output. So let's run. So here the main menu, as I shown previously in the task 2, we have student system and course system, but mainly for BST. However, for this task 3, I have added for BST data tree structure, and then display for data tree structure. So we have two versions, which is BST and display. However, right now we will be just looking at the benchmark BST versus display. So we will choose number 5 here. So here the output. So this is the output for this time run only. As I mentioned in the previous slides, this output is depends on the computer. So the output will be different each time. So here the comparison, which is 500 students for insert and search, 10,000 students for insert and search, which is for BST and display. Same goes to 5,000 students and 10,000 students. So when benchmark is complete, it is done. So how I managed to create the plotted graph? I copy this data into Excel and run the graph. Then this generate the graph, sorry. So here we are going to exit the system. So code execution is successful. That's all. Bye-bye. We're going to the next slide. Here are the actual results captured from the console during execution. So let's analyze the number closely. So at 500 students, n equal to 500. So insertion BSA took 1271 microseconds. So display took only 253 microseconds. So while search, BST took 444 microseconds and display took 185 microseconds. So the observation here, even at this small size, SP is already outperforming BST significantly. Next, at n equal to 5,000 students. So in insertion, BST jumped to 8,269 microseconds, while SP was 1,662. In insert, BST requires 3,990 microseconds. SP only required only 1,260, which is much faster. So the observation here is the gap is widening. The BST is roughly 3 to 4 times lower than the exploratory here. And then at n equal to 10,000 students, which is our largest test data sets, in insertion, BST took 20,354 microseconds and SPay took 4,117. In insert, BST took 11,334 microseconds, while SPay took 2,572. In the observation here at 10,000 records, what we can conclude is that the difference is really massive. The SPT is maintaining efficiency while the BST insertion time has skyrocketed. So to visualize this better, let's look at the plotted graph here. However, I would like to add and justify that the output in the previous slides and this slide is basically the same. However, I would like to mention the output that have generated here is during my first time run the code. So so in the future, if by chances we run the code again, the value might be different because these values depend on on our CPU clock speed, background processes, random tree shapes, memory cache, and operating system noise. So let's continue. In the left side, graph 1, which is for the insertion performance. So the blue line represents BST, while the orange line represents the SP3. Same goes to the graph 2 on the right side, which is for the search performance. So let's go back to the graph 1 again. So as you can see, the BST line shoots up really linearly and steeply. It approaches to 20,000 microseconds at the 10,000 students. However, the SP3 has a much gentler shape, gentler slope, which is remaining below 5,000 microseconds. So this proves that for creating the tree structure, SP is significantly more efficient in this implementation. So on the graph 2, at the right side, we see a similar trend as the graph 1. So this confirms that our self-optimizing theory, because we are searching for records that we were just inserted or frequently accessed. So the SP3 keeps them near to the root, making search time incredibly fast, which is back to the amortized to O log n. So, in conclusion, this project has successfully demonstrated the impact of choosing the right data structure. So, number one, BST is simple and effective, but for small data, because we saw it decreased without balancing mechanisms, while exploratory proved to be superior in this specific simulation. It provides self-optimization via S-playing, ensuring that the frequently or recently accessed nodes are easy to reach. So, our experiment conclusively showed that S-play is faster for repeated search, and space scales better for the large data sets. And then so this assignment highlights that when designing system for speed, efficiency, and scalability, a self-adjusting tree like SP3 is often a better choice than a standard static PSC. Thank you so much. That's all from me. Bye bye.